You're holding a glass of water right now, or maybe you have an ice cube floating in your drink. It seems completely normal. Ice floats. Of course it does. You've seen it 1,000 times. But here's the thing. Ice floating is actually one of the strangest phenomena in the entire universe. In almost every other substance, the solid form sinks in the liquid. Solid iron sinks in molten iron. Solid butter sinks in melted butter. Solid candle wax sinks in liquid wax. Even solid alcohol sinks in liquid alcohol. But water breaks all the rules. And if it didn't, if ice sank like every other solid substance, we wouldn't be here to notice. In fact, almost no life would exist on this planet at all. Today, we're going to explore why ice floats, what makes water so weird, and how this single oddity shaped the entire history of life on Earth. When most substances get colder, their molecules slow down and pack closer together. Heat is just molecular motion. When things cool down, molecules move less, settle into tighter arrangements, and the substance becomes denser. The solid form sinks in the liquid. Simple physics, right? This is true for almost everything in the universe. But water is different, spectacularly, bizarrely different. Each water molecule looks like a tiny V, with an oxygen atom at the point and 2 hydrogen atoms at the tips. The oxygen atom is greedy for electrons. It pulls them close, giving itself a slight negative charge. The hydrogen atoms end up with a slight positive charge. This means water molecules are like tiny magnets. The positive end of one molecule attracts the negative end of another. Scientists call these hydrogen bonds, and they're surprisingly strong for such small-scale forces. They're the reason water has such a high boiling point, why it forms droplets, why it climbs up the sides of glass containers. When water is liquid, these bonds constantly form and break. The molecules tumble past each other in a chaotic dance, packed relatively close together. But when water freezes, something remarkable happens. The molecules slow down enough that the hydrogen bonds lock them into a specific crystal structure. But here's the catch. This structure actually spaces them farther apart than they were in liquid form. The bonds force each molecule to hold its neighbors at arm's length, literally creating more empty space inside the solid than in the liquid. Think of it like a crowded dance floor. When everyone is moving, bumping into each other, they pack tightly together. But if everyone suddenly stopped and held hands with arms fully outstretched, they'd take up more space. That's exactly what water molecules do when they freeze. They spread out into an open, hexagonal structure, the same pattern that gives snowflakes their famous 6-sided symmetry. Every snowflake you've ever seen is a monument to this molecular geometry. The 6 arms grow outward because water molecules can only lock together at specific angles, 104 degrees to be precise. That angle forces the crystal to branch in 6 directions. No 2 snowflakes are identical, but they all share the same fundamental architecture. This expanded structure means ice is about 9% less dense than liquid water, and that's why ice floats. Water is one of the only known substances where the solid is less dense than the liquid. So let's talk about why this matters, not just for trivia nights, but for the entire history of life on Earth. Imagine a world where ice followed normal physics and sank. What would happen to a lake in winter? The surface water would freeze, and that ice would immediately sink. More water would be exposed to the cold air, freeze, and sink. Over and over, until the entire lake froze solid from the bottom up. Every fish, every aquatic plant, every tadpole and turtle would be trapped in solid ice. They would die. In our actual world, something miraculously different happens. When air temperatures drop, the surface water cools and eventually freezes. But that ice floats, forming a protective layer on top. This layer acts like a blanket, insulating the water below from the freezing air. The water beneath stays liquid, hovering around 4 degrees Celsius. Fish survive the winter swimming slowly beneath the ice. Frogs burrow into the mud. Life persists, even in the harshest conditions, waiting for spring. Scale this up to an entire ocean. If ice sank, polar oceans would freeze from the bottom up, eventually becoming solid blocks of ice miles thick. Ocean currents, which rely on temperature differences to circulate water around the globe, would shut down entirely. The marine food web would collapse. The planet would be locked in a permanent ice age. But because ice floats, polar ice caps form on the surface, reflecting sunlight while oceans beneath remain liquid. Ocean currents continue to circulate, carrying warm water from the equator toward the poles. This global conveyor belt regulates temperatures across the planet, making large portions of Earth habitable. When Earth went through its early snowball Earth periods, episodes when ice covered even the equator, floating ice may have been the key to survival. If ice had sunk and locked away the oceans in solid blocks, life might never have recovered. But because ice floated, there was always liquid water somewhere beneath the ice sheets, near volcanic vents. Life clung on in these refuges. When the planet eventually warmed, life was ready to flourish again. This doesn't just apply to Earth. When scientists search for life on other worlds, they look for liquid water. Moons like Europa and Enceladus, with subsurface oceans hidden beneath icy crusts, are exciting targets for astrobiology, precisely because water can remain liquid even when ice is present. The ice above acts as a shield, protecting the ocean below. This property of water also shapes climate. Because ice floats, it forms vast white surfaces at the poles that reflect sunlight back into space. Scientists call this the albedo effect. Sea ice reflects about 80% of incoming sunlight, while dark ocean water absorbs more than 90%. Without floating ice, more sunlight would be absorbed by dark water, accelerating warming in a dangerous feedback loop. As ice melts, more dark water is exposed, which absorbs more heat, which melts more ice. This is why Arctic sea ice loss concerns climate scientists so deeply. It's about the entire planet's temperature regulation system. And here's something most people never consider. When you squeeze ice under enormous pressure, it can actually melt, even below freezing. The pressure forces molecules closer together, collapsing that open crystal structure back into liquid form. This happens deep inside glaciers, allowing them to slide slowly downhill. Skaters experience a tiny version of this effect. The pressure of a thin blade creates a microscopic layer of water, allowing smooth gliding. Here's the mind-bending part. There are at least 18 different forms of ice, each with different crystal structures. The ice in your freezer is technically called Ice E. The H stands for hexagonal. But deep inside planets, water can form exotic types denser than liquid water. Ice 7, Ice X, Ice 18, these might exist inside moons like Ganymede or Titan. The next time you enjoy a cold drink, those ice cubes aren't just cooling your beverage, they're demonstrating one of the most important properties in the universe. If water behaved like almost anything else, those cubes would sink. More importantly, your ancestors would never have survived ancient winters, and you wouldn't exist. About 60% of your body is water. The blood pumping through your veins, the tears in your eyes, the sweat on your skin all depend on the same molecular dance that makes ice float. So the next time someone asks why ice floats, you can tell them, water molecules hold hands when they get cold. They spread out into beautiful crystal patterns instead of huddling close. And because they do, because water broke the rules, life on Earth became possible. In a universe of rigid physical laws, water found a loophole, and we should all be grateful that it did.